So for a wind turbine, the main objective is to extract as much of the kinetic energy as possible from the wind to convert into mechanical energy and later on into electrical energy. So the maximum that it can be extracted from the kinetic energy of the wind is the main goal of a wind turbine. In order to do that, if you look at this example here, if we have a 100% efficient wind turbine efficiency, so if we have a velocity of the wind and this is the wind turbine here, so in order to extract 100% of that energy, kinetic energy, then this wind turbine has to be stopped. It has to stop and has to extract all the available kinetic energy. So it will not allow the wind to flow through the other side. All right, so that is 100%, and that's not a good way because you have to block, and so there is not continuous way of energy production. Now, if you want to allow, if you don't want to block or you just want to block as little as possible, so it means that, for example, in this side here, there's a wind, and then this is the turbine here, the rotor blade, and then you allow as much air to pass through the turbine. Is not also an ideal case. All right, so you don't want to do that because if you allow a lot of, this is V for example, and this is V sub 0, and this V sub 0 is quite high, it means that the extraction of energy coming from the kinetic energy is low if you allow like that, if it's high V sub O. All right, so the answer to, in order for us to have a good efficient turbine, is to have in between these two situations, not stopping and also not allowing too much wind to flow through the turbine. So the in-between situation is to just allow a certain amount of wind to flow through the turbine in order for the blades to continuously how to say, rotate and extract energy. So through this, if we say that the wind that is flowing through after the turbine is V sub O, this one here, and the initial wind that is going towards the turbine is V, the ratio of this, all right, so it means that we don't want the V sub O to be too high and we don't want it to be zero as well. The ratio of this, based on some calculation and experimentation, is based on what we call as bits limit. So this part here is the theoretical maximum efficiency. So 59%, or through the power coefficient, so this is V sub O over V. So this is the ratio between the two towards the production of the bits limit. All right, so the bits limit is the theoretical highest efficiency of a wind turbine. Okay, so this is efficiency wind turbine. Now, but this theoretical is, again, is theoretical. There's a lot of various factors that limits your achieving this very high theoretical limit. So normally around 80 to 80% of that bits limit is the actual efficiency of the turbine. So we are talking about around 40 to 50% efficiency of most of the turbines available here, right? So in other words, based from this bits limit, not all power in the wind can be extracted. Some of the kinetic energy is carried downstream of the turbine in order to maintain airflow. All right, so that's why it's important that there should be airflow so that the rotor and the blade will continuously extract energy. Otherwise, if you stop it, then there's no continuous flow of or harnessing of energy. In this figure, we're showing about the efficiency of the different designs of a wind turbine. So that only the most popular one is the three-bladed design rotor here, and we also have a two-bladed and even a one-bladed rotor, as you can see from here. And we also have the vertical axis wind turbines like the Darius motor, We have the old design of a Dutch windmill here. We have an American wind turbine with this design. And so different designs, different blade designs, for example, will result to different efficiency. So in this case, in fact, the two-bladed design is a little bit higher in efficiency compared to a three-bladed design here for a horizontal axis turbine. And this is the bits limit or the maximum theoretical limit for efficiency for the wind turbines. But as you can see, if you look at the one-bladed rotor design, it's still high in terms of efficiency, more than 40%. But because of the design of only one blade that is turning around, you have to ensure that the tower and the foundation are strong enough, because this will also result to some form of imbalance when it is rotating around. So there's an issue of that one. And the similar thing for the two-bladed design. There could be, it's quite fast because only two blades. You can have a really high speed blade design. But if in comparison in terms of robustness and try to have a long-term operation, the three-bladed design is around 40 to 42%, which is not so far from the two-bladed, which is around 45%. This one is considered to be the best design so far, and the most common one that is being used now for horizontal axis design. So that's why for three-bladed rotor design, we had an efficiency of around 40 to 42%. This efficiency is basically based on the tip speed ratio. So when we say tip speed ratio, it is the ratio of the speed of the fastest moving tip in the blade or rotor uh, to the actual wind speed. All right. So the fastest tip of the blade of rotor to the actual wind speed is the tip speed ratio. So based on that ratio, we can get the efficiency of the various designs of the wind turbines. All right. In the generation of electricity from the wind turbine needs to be controlled in such a way that it can optimize its output. So that's why there is what we call as cut-in wind speed and cut-out wind speed. These 2 points in here in this graph. So in this way, to maximize the energy that is produced by the wind, the yaw system here, the yaw mechanism, is the one responsible for orienting the wind turbine, this part here, towards the direction of the wind. So if the wind is coming from this side, the wind turbine will face the direction of the wind. If the wind is coming from this side over here, for example, if the wind is coming from this side, this yaw mechanism here will also turn the turbine towards the direction of the wind. So the system will be facing now towards the direction of the wind. So this yaw mechanism or the yaw system will be very important in providing the direction of or orienting the wind turbine towards the direction of the wind so that it can maximize the amount of energy that is produced. So based from the graph here, so the cut-in speed for this graph, for example, is somewhere here, and the cut-in speed, wind speed, refers to the minimum wind speed that the wind turbine will be able to generate electricity. So if we are below that, this part over here, it means that the wind turbine will not generate any electrical energy or any power due to the lack of wind. So on the x-axis is the hub height wind speed. So the higher the wind speed, the higher will be the power. So this is the power output here. But if you look at the graph, the rated power of the wind turbine is this part here. So it means from this part over here, it has already achieved the rated power. So it means the rated power is the maximum power or the maximum capacity of the wind turbine. So let's say the maximum capacity is 1 megawatts of power. So this is the highest possible power output that this wind turbine will be able to generate. So even with the increase of the wind speed up to 25 meter per second, the rated power is still the maximum, is still the highest one that's possible. For in this case, this is wrong. This should be 2 megawatts, for example. So because this is 2000 here, so that is the maximum rated power. So what happens in this area here? Because as we know, if you remember, our formula for power is 0.602 times the efficiency times the area times the cube of the velocity. So if you can see from this original formula, it means that the higher the velocity or the wind speed, the power should go up. But in this case, it has maintained constant. So what happens here is that during this part here, as the wind speed is getting higher, the orientation of the blades of the turbine is actually changed in order to make it less efficient. So the orientation of the turbine is changed in this area here so that the efficiency will go down. So once the efficiency is go down, even though the speed is higher, because of the lower efficiency due to the turbine orientation of the blades, so it means the lift and the lift effect is reduced, then the power is maintained at the rated power. This ensures that it has to be regulated. So the speed has to be regulated in order by adjusting the angle and the pitch of the blade, so that to reduce the occurrence of damages in the wind. In any case, the rated power is the maximum that it can produce for that specific turbine. This part here, the cutout speed, is basically the maximum speed that is able for the turbine to function properly. Beyond this speed, for the usually is 25 meters per second. Beyond this speed, there is a great chance that the turbine will be damaged. So this is above the rated power. So if too great, the wind turbine applies the brake and shut down. So beyond this one, there is a brake system in the brake here. So it will apply the brake over here, and then the wind turbine will shut down in order to protect it from the risk of damage of the blades and the generator mechanism. So the two things here, two terms. The cut-in wind speed is the minimum wind speed that can generate electricity. In this case, it's around 4 meters per second. And for the maximum power is at around this part over here. No, not this one. Some part over here until this part here. So it's around 13 to 15 meter per second. So we can generate the rated power already at that point. And then once it reaches 25 meter per second, which is the cutout speed, then the wind turbine will shut down so that it will protect the whole system will not be damaged. So please remember that the wind turbines are actually changing in its direction depending on where the wind is coming from. So it will rotate because of this yaw system here. So it will also rotate to the direction of wind so that it can maximize. So imagine if this is fixed, if the wind turbine is fixed, if the wind is coming from this side, it means that it will be very less efficient. So that's why this yaw system is a good way to redirect or reorient the wind turbine towards the direction of the wind. So please remember that there is a cut in wind speed and there is a cut out wind speed in order to protect the system from damage.